Now let's talk about intermolecular bonds. Okay. Now intermolecular forces are forces that happen between molecules. Okay. Now there are three of them. When I say between molecules, I mean between molecules of the compound. You have to be very clear on that one. Now, intermolecular bonds is different from intramolecular combination. Now, intramolecular is within one molecule. For example, H2O is bonded by, remember we draw it like this. So this bond, this one here is called covalent bond and it is intramolecular, okay? But the one we are talking about here is intermolecular, okay? Among is among so let's look at something like oxygen, oxygen, hydrogen. Then there's another oxygen, hydrogen. That means there is water, there is water. So there's an interaction between these, and there is an interaction between these. Okay. So the interaction between this hydrogen and the oxygen is intermolecular bond. Okay. So intermolecular bond is broken into three parts. We have the one that is called the induced dipole to dipole moment or interaction. Induced dipole to dipole. It has a lot of names. You can call it induced dipole, you can call it dispersion force, you can call it London force, you can call it Van der Waals force. It is still the same thing. Induced. Okay? Induced has many names. That's induced, dipole to dipole. We have Van der Waals forces. You can call it dispersion forces. Okay? When you see any of this, it implies the same thing, and I'll break down the summary of it now. Induced dipole to dipole start with what we call instantaneous dipole. So I'm going to use like three atoms to explain it to you. I'll draw imaginary three atom. Okay. So let's say this is one atom, this is the second atom, this is the third atom, and I'm going to draw them again in three situations. So I'll use to explain. Now I'm going to use the first one. So remember, atoms are made up of electrons that are orbiting around the atom. Okay, and I have to tell you that electrons are never orbiting in fixed position. They are continuously moving. Okay, so don't think about them as they are fixed in position. I'll have to draw them 4 times so that the explanation will be clearer. Now this is another atom. Now all of them have their electron enjoying themselves. Okay, yeah. So they are randomly moving up and down in the shells of an atom. Now, because they are moving randomly, anything can happen. They can kind of accumulate at one end in one of the atom. They can tend to be pushed to one end. Okay, they can tend to be pushed to one end. Now remember, when they tend to be pushed to one end, there will be more of electron in one end. The other hand will have little or no electron. Okay, in that sense, the other hand that have more of electron will have more negative. Okay, to write that in chemistry, write delta plus, delta negative. Okay, telling you that this end in which the electron has accidentally migrated to has more negative charges, so we put negative charge there. Now the other hand in which electron is devoid of it, we put delta positive. Now this situation in which the electron accidentally accumulates at one end of the atom, leaving the other end partially positive, is called instantaneous dipole to dipole moment. Okay, instantaneous dipole. Okay, di means two poles, plus and minus. So instantaneous dipoles can only happen in an atom, okay, or a molecule. You cannot have instantaneous dipole in 2 or 3 or 5 atoms. No, it can only happen in one. Now, because of the behavior of this, and remember, electrons tend to repel each other, okay, because this is negative now. The electrons here will be pushed because this is negative, and remember the electrons here were negative, so they will be pushed to the other end as well. They will be repelled by this electron accumulating here. I want to highlight it with a different color. Okay, they will be repelled by the electron. The electrons here will be repelled towards this place. So it implies that the negative charge here will cause the electrons here to move to the other end. So that means this one also behave like the other one. The end here will now have more negative. The other hand will also have more positive. So we write this delta negative, delta positive. So because this situation is caused by this, we call it induced dipole moment. Okay, it is the first atom that is inducing or causing the dipole in the second atom. So we call it induced dipole moment. So that means instantaneous dipole moment in the first one is going to cause induced dipole moment in the second one, the second atom. Now the induced dipole moment again will now induce another dipole moment in the next atom. So remember the same thing will happen because this place has accumulated negative, it will push electron of this one also to the other end. To push electron of this one also to the other end. Now that means this one also become delta negative and delta positive. So all these situation in which instantaneous dipole creates or induce dipole in the corresponding and next atom, and that continues, that is what we call that is what caused what we call London dispersion forces. Now all these dipole will now start attracting to each other. Okay, remember that this end has become delta negative and this end has become delta positive. What I mean by the end of this one has become delta negative, this one has become delta positive, delta negative, delta positive, delta negative, delta positive. So the attraction between this delta positive and delta negative and this attraction are called the London dispersion force, or we call the induced dipole to dipole moment or interaction. You get the idea. So that's about induced dipole to dipole. Now, one thing that you must know about induced dipole to dipole is that it is present in all elements. Okay, all elements have it. There is no one element that does not have induced dipole to dipole moment. So that should be taken care of. You should know that. Now, the induced dipole to dipole moment is dependent on the number of electrons. The way I've been explaining, you know that it would be sensible to think that it depends on the number of electrons, because I just told you that it induced electron is pushed to one end. That means it is more dependent on electron number than any other thing. Okay, that's one thing you must know, and it is present in all elements, in all atoms. All atoms can exhibit um, induced dipole to dipole moment or London dispersion forces. Now, the more the London force is going to be present. You know that. That's common sense, because I just told you that it will push the electron to one end. So it implies that the more electron is pushed to the other end, the more charge it becomes, and the stronger it becomes. So it is dependent. So let me say London force is dependent on the number of electron. Okay, it's dependent on the number of electrons. So let's give a very simple example. In elements like hydrogen chloride and hydrogen bromide, which one do you think would have a stronger induced forces? Let's think of it. Bromine has a larger atomic number. I can't remember. I'm pretty sure it's greater than, it's going to be something like 40 something. And chlorine is just 17. So hydrogen is one. So that means one electron plus like 17 electron. And one electron plus like, let's say, I don't know, it's probably going to be more than 30. So let's say 35, I'm not sure. So that means this one has 36 electron, this one has 18. Definitely, in this compound, I expect to have a longer or a stronger London or London or induced dipole to dipole moment. I think that one is clear now. Now let's go to the next one. You can read the information I put below here. Now you can see now why is the boiling point of xenon, because I give some examples there so that you can, these are the questions you can see under this text. Say, why is the boiling point of xenon greater than that of krypton? Now, xenon and krypton are examples of noble gases. Okay, the examples of noble gases. Um, Krypton comes before xenon. So the noble gases are helium, neon, argon, krypton, then xenon. That's the order of the noble gases. These are the 5 noble gases that we have. Now the question is, why is xenon having higher boiling point than krypton? Okay. Now you might want to think of it as, oh, of course, now xenon has higher oxidation and higher electron number. That's the answer. It has more electron number and therefore experience stronger London forces. You can see that's the answer. It's as simple as that. So they can give you questions or whatever, but it's going to come in that sense. Now the second one is, once you understand that, now you can use that idea to do the permanent dipole to dipole interaction. Now the permanent dipole to dipole interaction is a little different because for any compound to exhibit permanent dipole to dipole interaction, it must be a polar molecule. Okay, I have to mention that it must be a polar molecule, and that was why I mentioned something about polarity, polar bond and polar molecule. Remember, that was when I cited example of something like ammonia. Ammonia as gas as it is polar. Okay, hydrogen like this is going to go like this. It's going to go like this. It's going to go like this, and because they are all heading in the same direction, there is no way it can cancel out each other. So it will be a polar molecule, and you draw a line from this to show the direction of the polarity of the bond. Okay, now this compound, for example, can exhibit what we call permanent dipole to dipole. So that means the first thing is it must be a polar molecule before you can decide if it will be a permanent or not permanent dipole to dipole moment. Okay, now back to the explanation. Okay, now permanent dipole, there must be a difference in the electronegativity. That means there must be polarity of the bond. When you have difference in electronegativity, that means the molecule in question will exhibit polarity, and the dipole moment in a molecule causes the interaction with the dipole of another molecule. Now, this is what happens. I'm going to use HCl as an example. I can even use ammonia that I was using as an example, just the same way I explained um, induced. Okay, let's talk about permanent. So HCl will be easy to use. The same thing with ammonia, but let's use it as a short molecule. HCl has dipole moment. Remember, the arrow is like this for HCl. Is polar. Is a polar bond and is a polar compound. Now, this HCl, there is another HCl here with another dipole moment. Now let's do delta positive, delta negative, delta positive, delta negative. Now delta negative of this molecule can interact with the delta positive of this molecule. Now because the dipole moment here is permanent, it's not instantaneous. It's now interacting with another permanent dipole moment. So that in that situation, it is called permanent dipole to dipole interaction. So it happens between polar compound or compound that have permanent dipole interacting in when their opposite charges interact. When they attract each other, you can say that is permanent dipole to dipole. I think that summarizes it. It's just when you have, now there are 3 points there. Number one is that the compound involved must be polar. Okay, it must be polar. That means it must have a polar moment. It must have a dipole moment. Now the polar moment must be permanent. Okay, that means it must be a permanent dipole moment. And the third thing is that there must be an interaction between the molecules, not the atom. Okay, between the molecules of the compound involved. Okay, the interaction between the positive partial positive charge and the partial negative charge of the compound involved. That will give us a permanent dipole to dipole. Now, what's the application of this to everything? Just like with the way we add questions on London forces. What can we find out about this? Now, a very good example that you may come across is this. Explain why the boiling point of trichloromethane is lower than that of CCl4. Even though, I think you should try to understand this question. Even though trichloromethane is polar with London forces, why CCl4 lack London forces? Now, let's try to identify. Um, Remember, London force is instantaneous dipole to dipole moment. Instantaneous dipole to dipole moment. Okay. Um, what that implies is that this question is not correct. I think I made mistake there. I wanted to say is a polar molecule with permanent dipole to dipole, not London forces. Remember all compound I mentioned that all compounds have London force. Okay, in fact, it's not even gone far. So that's a mistake. I wanted to write um here should be permanent dipole, and here should be permanent dipole. Okay, I'll explain that later. But look at this statement. All atoms or molecules experience London force. So if I now say this one lack, that means I'm contradicting the initial statement, which is not true. Every compound have London force. Okay, know that. So this should be permanent dipole to dipole. So now let's rephrase the question. Now explain why the boiling point of CHCl3 is lower than CCl4, even though CH3 is a polar molecule with permanent forces, permanent dipole to dipole forces, while CCl4 lack London force and lack permanent dipole. So let's explain if it's true that CCl4 does not have permanent dipole to dipole. Cl. Now let's try. Is this a polar molecule or not? Remember the bond will go like this. So this will cancel out each other. So this compound is non-polar. And I told you any compound that will exhibit a permanent dipole moment must be a polar molecule. And this is not a polar molecule. Definitely it can never exhibit a permanent dipole to dipole moment. And that is what this statement is saying, that why CCl4 lack permanent dipole to dipole moment. You get that now? So it doesn't make sense because this one does not have dipole moment. CCl4 does not have it. It still have a larger boiling point. The one that have dipole to dipole moment still have a lower boiling point. Does that make sense? You see, that's the question. That's what the question is trying to find out. Does it make sense to you that something that does not have a bond have a higher boiling point, while the other one that does not have a lower boiling point? Let's see if the answer is justifiable. Now, the number of electrons in CCl4 is greater than CHCl3. Now you can calculate that. CCl4, one chlorine is 17. 17, there are 4 chlorine here. That means that's 17 times 4. Now, plus 12. That's the number of electrons inside CCl4. Now, here, it is 17 times 3 plus 12 plus 1. You definitely know that will be 16 less than this one. Because there are 4 17 here, there are 3 17 here. So, common sense should tell us that this one will be CHCl3. CHCl3 will be 16 less than this one. You know, this one is 17 times 4 plus 12. This one is 17 times 3 plus 13. So you should know that 1 is added here. 17 is lost here. So 17 minus 1 will give me 16. It's a simple mathematics. Now, so it explains that CCl4 will have a stronger London force. CCl4 will have a stronger London force than CHCl3, and that is why it has a higher boiling point. So whenever you are answering any question, you must always consider other forces. Remember, there is not only one force that is acting, there are a number of forces acting on the body. Okay, now this is another question which I like this. I said we should explain the table. I want you to carefully look at the table. Explain the table below. Hydrogen halide, HCl, HBr, HI, then number of electrons, then boiling point in degree C. Now, you understand that minus 35 is greater than 66, okay? And minus 66 is greater than minus 85, so don't get it twisted. Now, by this information, it tells us that the boiling point of halide, hydrogen halide, HI is the greatest. This one have the highest boiling point, while this one have the lowest boiling point. That's the meaning. And this one have the least number of electrons. This one have the most number of electrons. You should have understand the answer already. The same explanation I give for the previous question is what I'm going to give you again. Hydrogen halide have more electrons, so there is more London force. Okay, more electron means more London force. Okay, more electron means more London force. So that means this 54 will have more London force than every other one. Therefore, it will have the highest boiling point. Okay, that's the same explanation. Although, if you look at their permanent dipole to dipole moment, all of them have permanent dipole to dipole moment, and it decreases down. Okay, it decreases down because in polarity, you remember the polarity is a factor of electronegativity. Okay, and I think I explained that here below. Permanent dipole to dipole moments, like if you look at this explanation I put here, I said when you want to explain it using permanent dipole, you say that HCl has a stronger permanent dipole to dipole moment than HBr and has a stronger than this because of decreasing electronegativity of the halogen. Now, chlorine is more electronegative than bromine. Bromine is more electronegative than iodine. So that means the permanent dipole to dipole moment will decrease. That means chlorine HCl we have the highest permanent dipole to dipole, while HI will have the least permanent dipole to dipole. That's the implication of that. But when we talk of London forces, it's the opposite of it. So, because the increasing number of electrons, so you can see that Hi have the highest London force, HBr have the second highest London force, HCl have the third highest London force. So when you compare the three of them together, we say that Hi is the most is the compound with the highest London force. So we can expect that to have the higher boiling point. Okay. Now the last but not the least is the hydrogen bonding. Okay, hydrogen bonding. Now the hydrogen bonding is pretty straightforward. Just think of it as NOF. Okay, whenever hydrogen have a relationship with NOF, okay, whenever hydrogen have a relationship with any of these elements, NOF, nitrogen, oxygen, and fluorine. Those are the three most electronegative elements on Earth. Okay, three most electronegative elements on Earth. And if we were to rank the three of them, the strongest of all of them is also fluorine. So if I want to say which element is the most electronegative, I would say fluorine. And if they ask me which one is the most electropositive, I would say potassium. Okay. Electropositive is potassium, electronegative is fluorine. So let's continue. Now, having that at the back of our pretty mind, we now know that hydrogen, when it's bond with any of these elements, it forms hydrogen bonding. That's not really the definition. Let me explain that to you clearer. It doesn't mean that when I have hydrogen bonding with oxygen bonding with hydrogen, this is hydrogen bond. No, we are talking about intermolecular bond, between molecules. So what I'm trying to say is that it is only when hydrogen bonds with oxygen bonds with hydrogen, then another situation like that is here. Then the oxygen of this molecule now interacting with hydrogen of the opposite molecule. That's what they call hydrogen bonding. When the oxygen from one molecule, different molecule, is combining or they are interacting with hydrogen from the another molecule. So let me give another example. Let's give the example of can we have it in ammonia? Ammonia, yeah, yeah. Okay, no, we can't have it in ammonia molecule. Okay, hydrogen fluoride, yeah, that's a good one. In HF, hydrogen fluoride. This is one molecule. Let me arrange them like this. Hydrogen fluoride. So hydrogen fluoride. Hydrogen fluoride. So you can understand. I flip them directly. Okay, so that you can see. Now, this is one molecule. This is another. This is another. This is another. Now, the fluorine from here will interact with this. This one 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 will interact with this. Now, the interaction between different molecules of hydrogen fluoride, not just interacting between them, the interaction between the hydrogen from one molecule and fluorine from another molecule is hydrogen bonding. So I've shown you the interaction between hydrogen and oxygen. Now I've shown you the hydrogen and fluorine now. Then let me show you the hydrogen and nitrogen. That we can do in ammonia. Nitrogen. So you'd see that there is no big deal in all these things. It's just that now there is a lone pair of electron there. Now there's another ammonia here. I'm going to put it in an opposite direction. Okay. I'm going to put like hydrogen here. I'm going to put like nitrogen on top. Okay. I'm going to put like hydrogen here. I'm going to put like hydrogen here. Now, the interaction between this hydrogen and nitrogen because they have different molecules of ammonia. Now this is one molecule of ammonia, this is another one. So the interaction between that hydrogen from one molecule and that of another is called hydrogen bonding. I think that is clearer now. Now, there are two conditions that hydrogen bonding can happen. Number one, it must involve all those electronegative elements I gave you. Remember NOF. If you forget anything, just think of NOF, or you say FON if you like, fun or NOF. Anyone is fine. So it must be between those elements. If it's not between those elements, you cannot have it. That's number one. Number two, that the most electronegative, the strongest hydrogen bond is found in hydrogen fluoride. Okay, that is common sense because fluorine is the most electronegative element. So you expect that the strongest hydrogen bond would be found inside hydrogen fluoride. That's the next thing. Another thing you must know is that if you are drawing hydrogen bond, it is very important that you write it like this. I want to show you clearly how you should do it. Um, there is a lone electron pair here, very important. So you will draw an arrow from hydrogen straight to the lone electron pair. It's very important. They can ask this in exam. If you are drawing the bond, it must travel from hydrogen to the fluorine. Can you see that? Okay. So it implies that the broken line is hydrogen bond. It's very important you do that. And again, you notice that there is no way there must be a bond electron pair. Okay. A lone electron pair, sorry. A lone electron pair on the electronegative element. Okay. If the fluorine does not have a lone electron pair, it cannot have hydrogen bond. And that explains why elements like hydrogen sulfide does not have hydrogen bonding. Okay, hydrogen sulfide does not have hydrogen bonding. Even though it's electronegative, it's in this group of oxygen, it still does not have hydrogen bonding. Okay, that's the gist about hydrogen bonding. The only thing that remains there is the properties of hydrogen bond that makes it relevant. Okay, now how does it helps to how does it make water behave anomalously? Anomalous behavior of water. Now, water is less dense than ice, rather. I put it in question. I say, why is ice less dense than liquid water? Those are the questions you may come across. Why water? Why does water has unusual high boiling point? Why does ice prevent water below it from freezing? Those are the three very important questions that you should be able to analyze. Now, why is ice less dense than liquid? There are two answers they want to hear. Number one, the ice um, is formed by the molecules of water bonding together by hydrogen and using hydrogen bonding to fix them together. So the hydrogen bonding kind of stabilize this ice, keep it in position. But but it does not only keep it in position, it also give it a reasonable space. Okay, it gives each molecule of water a reasonable space. So it doesn't fix them together. So let's say this is one water molecule, this is another water molecule, this is another water molecule, this is another water molecule. So the hydrogen bond between them will give them space. Give them space. So the space that gives them makes it floats on water. Okay? The space within them will give passage for air to flow in. And when air occupies something, that thing will weigh less. Okay? It's just the idea of upthrust. Okay? If air occupies a particle, that particle is most likely going to weigh less in air. And when it weighs less in air, it's most likely going to experience flotation. So that means that's why ice floats in water for two main reasons there. Now, why does water has unusual high boiling point? That's because of the presence of hydrogen bonding in its molecule, because it will require extra energy to break the hydrogen bond in the molecule. It will require extra energy to break the hydrogen bond in the molecule. Now, that answers that. Now, why does ice prevent water below from freezing? Now, that's one of the advantage of water icing. Is actually freezing of water during cool temperature is actually an importance to living organism in water. If water does not freeze and it doesn't float, the water under it could freeze up. The whole of the sea could freeze up, and the fishes and aquatic organisms there will die. So the ice serves as a barrier, like a cushion, like a layer to prevent the lower layer from freezing. So it's like a barrier that prevents the lower layer from freezing. So it's very important you understand those 3 points very well. I think that's all about intermolecular bonding.